If you stretch a blockchain network to maximize both the number of independent nodes and raw transaction throughput, the system inevitably snaps taut. The limits of distributed ledgers dictate that as decentralization increases, execution speed drops. To directly test the boundaries of that paradox, Interlink has launched the Taj Mahal testnet. The Taj Mahal environment operates as a strictly isolated, purpose-built subset of the eventual mainnet. Interlink's engineers and scientists designed this specific environment with a single directive: to independently validate the parameters required for high transaction throughput under live conditions. This diagram outlines a standard, monolithic Layer 1 blockchain. It acts as our control group. Notice the strict sequential path. Transaction data moves from the mempool, waits for consensus, and finally reaches execution. At each step, a structural data bottleneck forms. Understanding how the Taj Mahal testnet bypasses these traffic jams requires breaking down its architecture from first principles. We have to examine its tech stack layer by layer and compare it directly against these standard market solutions. Claims of technical superiority mean nothing without evidence. Viability only emerges when every layer is proven against the stress of a live, hostile testnet environment. The analysis starts at the bottom of the stack. Every distributed ledger relies on a foundational layer of peer-to-peer data propagation and network topology. This network topology map visualizes a standard gossip protocol. This is how legacy Layer 1 networks broadcast transactions. A single node receives a transaction and passes it to adjacent peers in a slow, randomized ripple. This randomized broadcasting creates latency overhead. Nodes receive the same data multiple times, choking bandwidth with redundant transmissions. The Taj Mahal testnet abandons gossip protocol in favor of a multi-path routing algorithm. Data jumps across the network in parallel, calculated streams. Instead of guessing which peer to alert, Interlink maps the physical and topological distance between nodes, continually predicting the lowest latency communication paths available. Because these paths are calculated in advance, mempool synchronization happens concurrently across specific civigraphic clusters, rather than waiting for global node-by-node discovery. Interlink also compresses transaction payloads, reducing the raw packet size. Looking at this dual line graph for global synchronization, the legacy gossip model scales exponentially over time. The Interlink routing protocol maintains a flattened curve, drastically reducing propagation time. This structure requires trade-offs. Maintaining constant topology mapping and ingesting concurrent data streams demands significantly higher baseline bandwidth and robust hardware resources from validator nodes. If the underlying network topology delays the arrival of transaction data to the validators, raw execution speed at the higher layers cannot compensate. The data must arrive instantly for the rest of the stack to function. We move up to the consensus layer. This is where those propagated transactions are validated and permanently ordered into the ledger. This timeline illustrates standard Nakamoto consensus, or sequential Byzantine fault tolerance. Blocks are produced one after another in a single, rigid chain, with a mandatory wait time enforced between each finalization. This single-threaded formation creates an unavoidable upper bound, limited by single block finality. The Taj Mahal testnet decouples this using a directed acyclic graph architecture. The single chain transforms into a multi-threaded structure, allowing producers to validate transactions simultaneously. Without a single leader, parallel threads introduce double spending risks. Interlink counters this through intersecting cryptographic voting paths. Nodes cross-reference parallel histories in real time, enforcing Byzantine fault tolerance without reverting to a single line. Older blockchains rely on probabilistic finality, where a transaction becomes more secure as more blocks are stacked on top of it. Interlink's consensus model provides deterministic finality. Once the parallel threads intersect and vote, the transaction is irreversibly settled. By mathematically guaranteeing settlement at intersection, the time to finality drops to fractions of a second, bypassing block wait times native to Ethereum and Layer 2 rollups. The current testnet phase is pushing this consensus engine through severe network partitions and simulated malicious validator attacks to observe exactly how the multi-leader logic holds up under peak stress. Removing the artificial bottleneck of sequential block production clears the path. The consensus layer shifts the mathematical speed limits of the distributed ledger upward, preparing the system for the final execution phase. We reach the top tier of the stack, the execution environment. This is where smart contract logic executes and state transitions occur. Standard EVM architecture dictates that every transaction must be processed one at a time, reading and writing to the state registry in strict sequential order. Push massive volumes of data through a single narrow pipe and pressure builds. Multi-threaded processing diverges that flow, separating the workload into parallel, fast-moving channels. The left shows a traditional single queue. The right shows interlink mapping transactions to independent subsets simultaneously. If transactions target the same data, they are flagged and routed sequentially. Unrelated transactions bypass them entirely, executing instantly. Processing thousands of state transitions concurrently forces the system to manage immense structural complexities. Updating the state tree at this velocity requires storage optimization to prevent network bloat. This localized concurrency enables a raw transactions per second ceiling that allows the interlink execution environment to compete directly with highly optimized chains like Solana and Monad in computational efficiency. The optimized network layer delivers the data instantly. The parallel consensus layer validates it. But the stack only achieves true architectural scale when the execution environment can process those state transitions exactly as rapidly as they are fed in. Zooming out, we can observe the holistic design of the interlink stack. The localized networking topology feeds data upward into the parallel consensus layer, which instantly passes it to the multi-threaded execution environment. The alignment of these specific engineering choices creates a system designed for high-velocity data processing and minimal latency. The Taj Mahal testnet remains an isolated, ongoing experiment. It represents one functional component within the full protocol design. Comprehensive tokenomic models, extended governance layers, and additional architectural modules have been excluded from this environment. They will be integrated when the final mainnet is assembled. Right now, Interlink's science team is continuously harvesting telemetry on validator metrics and edge case network failures to mathematically refine these core throughput mechanics. By physically proving these structural innovations in a live environment today, Interlink transitions its high-throughput research into a battle-tested baseline for the mainnet launch.